So, first we look at the least mean square adaptive filter or LMS filter. Now, the change what we do looking at that optimal filter. In case of optimal filter, we have actually taken that the expected value of E n square that we computed by the assumption of stationarity and the ergodicity of the signal, and we have replaced the expected value of the square of error as that sum of the error over the time. So, now as you know that thing cannot be done because we are dealing with non-stationary signals. So, we cannot have something called ergodicity. The simplest thing what we could do, we could drop the expectation operator and directly compute E square n. Now, by dropping that expectation operator, it gives us a huge advantage in terms of computation. Now, let us see how it proceeds. So, we expand E square n, we know that E n is that x n minus that the weighted the reference signal. So, that part that when we expand, we get these three terms. One is x n square and that we get cross between that x n and the y n that is generated out of the reference signal, and we get a term square term out of that reference signal here. So, now using steepest descent technique, what we need to do, at the next instant the weight W n plus 1, it should be W n minus mu times the gradient, and again because the process is changing over the time, the gradient is also having an index of n. So, here the mu is the step size which actually controls the stability and the rate at which it will converge to the optimal value, and this delta n, it is the gradient of the squared error with respect to the tap weight, because tap weight is the only thing in our hand that we can modify to get a better estimate of the noise. So, now that we compute the gradient of that error with respect to the tap weight, and we get it is minus 2 x n into vector r n and twice the dot product of the weight at the instant n and the reference input r, both are vectors, the dot product of these vectors into that the vector r n. Now, if we take this part as common out of these two, what we get? We get x n minus W t n into r n. So, this form we already know, this is very known form, this is our error at instant n. So, replacing this part in this equation, we simplify it, we get that the gradient is minus 2 E n into vector r n. So, now if we replace that estimate of the gradient of that error, we get here that the new tap weight at the instant n plus 1, it would be the previous tap weight, and the minus sign along multiplied with this minus, it gives us a plus twice mu, that the error at this instant, that is E n, into the vector R n, which is the reference signal vector. Now, this equation is our update equation, and this is known as Widrow-Hoff LMS algorithm. This simple equation actually we can use to update the weights, and as we keep on update the weights, it will actually keep on changing and latch to that the process, and if the process is changing, because the signals are non-stationary, so it will actually respond to that change, and by that updation of the weights, it will always try to remain to be a optimal filter. So, that is the simple idea about that the Widrow-Hoff LMS algorithm, which is very simple yet very effective, and that is the reason it is very popular in the academia as well as in the industry. So, now let us look at the special the attractions of the LMS algorithm. The first thing what we get, its simplicity and ease of implementation. Why we talk about the ease of implementation? The reason is, let us look at that signal, that what we get, the previous page, that update equation is so small and simple. What we need to compute? We need to compute that error. In fact, that is the output. So, in any case we need to compute that, and the reference vector of the reference vector for that interfering noise, that already we have taken to compute that actually that output of the adaptive filter. So, if we take the product of these two and scale it by 2 mu, that gives us the change in weight. So, it needs actually that here one multiplication, 2 mu is one scalar quantity, then another term is E n, and with that we are computing changing actually multiplying with R n, that is having dimension m into 1. So, that the number of multiplication it needs 1 to compute 2 mu into E n, and then m minus 1, rather we can say that m multiplications, that because R n is m dimensional vector, and then what we need, that m additions, because each of the component of that tap weight, it need to be modified. So, 1 plus m multiplication and m additions. So, they are actually very much lightweight, and that way the implementation is very easy and simple. Now, why we are so much actually worried about the simplicity and ease of implementation? The reason is, in case of adaptive filter, what we have proposed, that we are going to update W n. So, at each instant, that before the new value of say x n comes, That means, once we get the x n, we need to compute that W n before the arrival of n plus x n plus 1. So, we have actually that one sampling period, that is the maximum time to compute the weight. Now, let us look at the signal. If the signal is having a frequency, maximum frequency is 1 hertz, then we have 1 second time. If it is 1 kilohertz, then we have 1 millisecond time. So, you see that more and more the sampling frequency, that our computation also need to be more and more fast, and there it becomes very important that the algorithm what we choose, it is something that which we can implement in real time. So, that is actually one of the very big bonus for the Widrow-Hoff LMS algorithm. Now, let us look at the next point, the expected value of the LMS tap weights converts to the optimal Wiener solution when the inputs remains uncorrelated over time. That means, what it is suggesting, that if we have the input, that is something which becomes stationary at least over some time, it is not changing with the time, then we could have used the optimal Wiener filter. Now, this LMS algorithm will act as a that optimal Wiener filter, in the sense that we will get the same set of actually the tap weights, or the tap weights will convert to that ideal tap weights given by the optimal Wiener filter. The only condition what need to be maintained, that the inputs, that is the desired signal and the additive interfering signal, they should remain uncorrelated with each other over the time. So, this is the only condition on that signals. It does not demand that they need to be stationary or any other more condition. Now, the next important input, that we need to choose actually this mu, what is it, that is we call the tap weight, very carefully. It should be bigger than 0, because if we take it 0, then there would be no updation of the weight, and again we told that it should be less than 1. In the actually that it can be shown that it should be less than 1 by the 1 divided by the largest eigenvalue of the reference input autocorrelation matrix. The reference input R n, that with the help of that, it is a m by 1 vector. So, we can get the autocorrelation matrix of it if we take the cross with the same vector or multiply with 1 by m vector, that is transposed form of R n vector. So, it can give us the autocorrelation, and to get that autocorrelation we need to take the expectation of this, and if we compute the eigenvalue of this matrix, that mu should be less than 1 by that the largest eigenvalue of this matrix, and that is necessary for the stability of that LMS algorithm. Otherwise, what can happen, this LMS algorithm will never converge. So, we need to choose mu very carefully, and in practice that as you may not be able to compute the eigenvalues, usually it is taken a very small value and we try to keep it small, so that the stability does not come under any question. Now, let us see that what could be the impact of choosing the mu. That we get actually two scenarios. One is weight vector noise, another we call weight vector lag. Let us start with the second one, the weight vector lag. We told that we should be very careful in choosing the mu, and it should be very small, so that the stability does not come into question. So, if we choose mu to be very small, then what will happen? The updation or the rate of updation also would be very small, because whatever the change we are suggesting, we are reducing it by mu, by multiplication. So, we are taking that part of the change suggested. So, if we take mu to be very small value, as the updates will be small, if the process is changing, we will see the compensation is lagging behind, and the optimal that filter, that is our LMS algorithm, is taking time to adjust to the situation, and the error will actually come down after a lot of time. Whenever there would be a change in the process, that LMS algorithm will change, but because of its actually lack of speed in change, it will lag behind, and because of that, till it can catch up, there would be high error. Okay. So, that is something unwanted. On the other hand, if we increase the value of mu, what will happen? The updation would be faster, but in that case, that when we go near the convergence, and let us assume that we have chosen it in such a way that it does not cause any problem in the that stability of that filter, but as we have increased that mu, the updation is happening all the time even after the convergence. So, there will always be a change in the error, and after the convergence we see that the noise is more. So, that is called, actually that situation is called weight vector noise. That means, there is a noisy estimate we are taking for the weight vector, and that is getting reflected in the output as noise. And the main source of it is that at the beginning of the LMS algorithm, that there was an expectation operator on the error, we have actually dropped that, and this is the result of actually removing that the expectation operator or that smoothing operation there. Now, what could be the ideal situation then? You would like actually to have mu to change over the time. Initially, if the mu is little high, then we can update it quickly, and we can have actually low weight vector lag, and once it converts, then if we can reduce it, then we can get actually that less weight vector noise. So, both we can minimize. Usually for if we keep it a fixed value, then we need to get one of them. We cannot minimize both at the same time, but if we can update the value of mu, change the value of the mu appropriately, that means at the beginning if we can have little high value, then we can reduce the weight vector lag, and then once it goes to the convergence, if we reduce it, we can again reduce the weight vector noise. So, with that expectation, we come with a new update equation where the mu is changing over the time. And how it is changing? The constant mu divided by m plus 1. We know the m is the dimension of that vector, the tap weight vector, and we have a function x bar square, and it is actually a function of different thing. Here is something called alpha, a forgetting factor, then we have the reference, the signal Rn, and we have the previous value of that x bar square. Okay. And how it works? Let us look at that x bar square at the instant n. It is nothing but that the alpha, the part what we have taken as the forgetting factor, it is varies between 0 to 1. It is alpha times the instantaneous energy of the reference signal, and 1 minus alpha times the previous estimate of that x bar square. So, if we start with the situation where Rn was 0 before the start, so in that case what is happening? If we make alpha equal to 1, it will change directly with that reference signal, because there will be no contribution of the previous value of the x bar square. And if we make alpha equal to 0, then that there would not be any updation, because there is no contribution of Rn square, it will go only with the previous value of the x bar square. Now, if we choose in between a value, which would be the case, it will take some part of the reference input, as well as it is actually using the part of the previous estimate. That means, it will smooth out the change in the energy, instantaneous energy of the reference, and with the help of that we are updating the mu, and thereby we are able to actually optimize both the thing that we would like to have when the system is changing, less weight vector lag, and when it goes towards the convergence, that less weight vector noise. So, let us see some actually graphs which will help us to understand this concept. So, first we look at the scenario that we have taken a LMS filter where the value of mu is not that 1. So, 0.01 for this value, we get for this process that as it is moving, that there is a noise all the time in the error is fluctuating, but it is converging steadily, and before 2000 iterations it has converged. So, roughly we can tell that within 2000 iterations it has converged, and after that we see that minus 300 dB has become that noise power, and there is a small amount of fluctuations is there, which is that weight vector noise, and the lag in getting to that position, that is the 2000 iterations, that is the weight vector lag. Now, if we change this value, that if we actually make it even smaller, that 0.003. So, what is happening in that case? Instead of 2000, now it is taking almost 6000 iterations to converge. and it is again converging to the same value minus 300, and again there is some amount of noise which was there at the time of adaptation as well as after the convergence. So, what we get, the weight vector lag has increased by reducing the value of mu even smaller. So, we know that what we get, the message here, that if we keep on reducing the mu, it may not actually help us in any way. Now, let us look at the other scenario. If we try to reduce the weight vector actually lag and increase the value from 0.01 to 0.08. So, in that case what is happening? See that it is not in the previous cases, if we look at that the previous cases that compared to that, see in the previous two example it was directly going towards the convergence, the trajectory was smooth. Now, in this case the trajectory is no more smooth and it is a jerky kind of movement. It is going down again going up. So, moving away from that minima, again it is coming down again going up, and because of that nature it is taking more time, though it is not going up to 6000, but it is not actually that coming down by 2000, it is requiring more time, it is coming towards the convergence at 4000 iterations. So, weight vector lag in this case has not reduced, and associated with that we see that the error after the convergence that's also have increased. We see there is a movement above the minus 300 dB line. Overall error, if we look at here, the changes are more here. So, we see that by increasing the mu we are having more weight vector noise. So, that these three examples that helps us to get the importance of the choice of mu, and that if we can get that mu in a proper way, then we can actually have much faster response and lower noise. Thank you.